Good morning, everyone. So our first speaker this morning is Professor Anthony Nouy from University of Nantes. So he will discuss optimal sampling for nonlinear approximation. That's why I come here.
Thanks a lot, and thanks to the organizers for this invitation. So I will present a series of recent results that I have obtained with different collaborators, Robert Röke from Berlin, and Bertrand Michel and Philippe Trunschke from Nantes. So Philippe Trunschke is leaving Nantes now to Berlin again. And I will talk about different results about optimal sampling for both linear and then nonlinear approximation. I will try to tell you about some classical results and new results on linear approximation and show you how we can extend or use this machinery to do something in nonlinear approximation. So the setting is standard. We consider the approximation of a function f from a norm space V, and we want to approximate it in a subset Vm described by m parameters. Here, the approximation tool, Vm, is selected from some prior knowledge on the function f, and in order to obtain, hopefully, a fast convergence of the best approximation error. Okay? But the topic is here not to discuss about the choice of this approximation tool. I consider it is given, and we focus on the problem of constructing an approximation f hat m in the set Vm by an algorithm using only a limited number of information, and standard information being pointwise evaluations, but it's not limited to this, as you will see later. So we will say that an algorithm is quasi-optimal for a function class, is for any function from this class. It outputs an approximation with an error which is up to a constant, the best that can be achieved by the approximation tool. For random algorithm, and this will be mainly the purpose today, random algorithm, quasi-optimality can be evaluated in average if you have this kind of quasi-optimality property. We'll say that it is quasi-optimal in average. Okay, so when information is very costly, and this is the case in many applications, the challenge is to provide an algorithm that gives some quasi-optimality property with a number of samples which is very close to the number of parameters. And this will require us to adapt the information to the space Vm and to the target function class. Okay, so we are in a setting where we can play with the sampling. Okay, we can place the points where we want. In a statistical learning framework, we will call this an active learning setting. Okay, we can play with where we place the points. Okay, so we'll start with a few rather standard results on optimal sampling for linear approximation, then move to the exploitation of these techniques for nonlinear approximation, and then I will come back to linear approximation. Mainly, the first results, in the first part, will be related to quasi-optimality in average sense, and the last part, I will tell you a few results on how to get quasi-optimality almost surely. Okay. Okay. So let's start with a standard least square setting. So we want to approximate a function from L2 space of functions defined on a set X equipped with a measure mu. We have the standard L2 norm here. We are given an m-dimensional space Vm. And we will rely first on classical weighted least square approximation, where the approximation is obtained by minimizing this weighted least squares functional, where the weight here are denoted wxi minus 1, where w is a weight function that will have to be chosen in a suitable way. This is equivalent to optimizing a distance from the approximation to the function relatively to a semi-norm. Okay, and here the points have to be selected. So what we have to discuss is how to choose the points and how to choose the weights. Okay, these are the only flexible parameters here. If the points are chosen randomly and samples from a distribution with a density W with respect to mu, then you can see that this is nothing but an unbiased estimator of the squared L2 norm. Okay, so we have in expectation, the squared semi-norm, which is here, is equal to the L2 norm. And we can go further about the relation between this semi-norm and the L2 norm. If you are given an L2 orthonormal basis phi1 to phi m of the space Vm, then you have this equivalence between the semi-norm and the L2 norm for any element V in Vm. And the constants that are here are the minimal and maximal eigenvalues of the empirical gram matrix that you see here, where this notation phi bold is related to the feature map gathering the evaluations of the basis functions. Okay, this is a classical empirical gram matrix. So we understand here that the quality of least square approximation will be related to how far this gram matrix is from the identity. In particular, you have this relation between the L2 error that you commit. The squared L2 error is bounded by the best approximation error. This is the orthogonal projection of f onto Vm. And here you see a term where you have here the empirical norm of the best approximation error, and here the inverse of the minimal eigenvalue of the gram matrix. So in order to control the least square approximation quality, we will have to control this minimal eigenvalue of the gram and also the behavior of the empirical norm. So let's talk about random sampling here. If the points are sampled according to a distribution with the density W, then we have that the average of the expectation of the gram matrix is the identity. Moreover, if the samples are drawn independently from this distribution, then the gram is an average of independent matrices and identically distributed matrices that are written here. And these have a spectral norm, which is W minus 1 times the L2 norm of the feature map. And then, almost surely, the spectral norm of these matrices is bounded by this constant, which is a supremum over the set X of W minus 1 and L2 norm of the feature map. Okay? So this constant, in fact, is independent of the choice of the basis. Okay? It's a constant depending only on the space, Vm. And so, from classical results on classical concentration inequality, namely the matrix Chernoff inequality, tells you how fast this average of IID matrices converges to identity. Okay? And in particular, you have a result from Trop, and here adapted by Cohen and Migliorati, telling you that the probability that the minimal eigenvalue of the gram is less than 1 minus delta, okay, this probability is bounded by something going exponentially fast to 0 with the number of samples. But this rate here depends on this constant that you see here. Okay? So now you can play with this inequality and try to optimize the density W so that you minimize this constant and get the fastest rate here. And this optimum is reached for a density W, which is written here. Okay, minimizing this with respect to W gives you this density. It's a probability density function, 1 over m squared L2 norm of phi of x, written here also. And you may recognize, for those who are familiar with polynomials, this is a generalization of the inverse Christoffel function for polynomials. Okay, but here, generalization in the sense that here we can play with other functions than polynomials. Okay, so if you draw samples according to this distribution, okay, independent samples, then you will have the fastest rate of convergence, the fastest concentration to identity of your gram matrix. Okay, and this gives an optimal constant k equal to m. Okay, so here you will have an expression with a m here. Okay, gathering all of this, you get this theorem. Assume that your points are drawn from this independently from this optimal sampling measure, and assume that you condition these samples to satisfy that the minimal eigenvalue of your gram is greater than 1 minus delta. If the number of samples is greater than this number, okay, then you will have that the probability of this event is greater than 1 minus eta. Eta is a parameter which is here in this relation. And at the end, you get a result in expectation. The expected squared error is bounded by a constant times the best approximation error. Okay? So here we need a condition on the number of samples, and we need this conditioning in order to get this quasi-optimality in expectation. Just a comment about the fact that you can extend these IDs to other spaces than L2. You can extend this to Hilbert spaces of functions defined on X and equipped with a norm that can be written in this way as an integral of the squared norm of LXF, where LX is some linear map indexed by X. And for example, think about Sobolev spaces where LXF will just gather all derivatives up to an order S of the function f. But this will require another type of information. If you do least squares approximation for this kind of norm, okay, you will require an information which is LXIF, and in this case, it means you have access also to the derivatives of the function, okay? Evaluations of the derivatives. But then the theory is completely the same, and you get exactly the same result when the norm here is the norm that you see here. Okay, so in the condition you see here, if I summarize this, the number of samples that is required, that scales like m log m, delta minus 2, may still be very large compared to m. Okay, in applications, concretely, you can see that this number is far, far beyond the number of parameters. And a fundamental question is, can you reduce this number of samples? One way to do it is to rely on subsampling. There have been several strategies proposed in order to start from a big sample for which you have a stable gram matrix, and then you have an algorithm to downsample, to select a subsample from this and still get stability of your gram. Okay, this is a possible approach. Another route is to introduce a sampling, which is no more an independent sampling, but you introduce dependence between the samples in order to better control the spectrum of the gram matrix. I would like to mention a recent work by Schkifa and Dolbeau, Mathieu Dolbeau, who is here in the room. They introduced a sequential sampling algorithm inspired by the subsampling strategies that have been used in this paper. And this strategy yields quasi-optimality in expectation with minimal oversampling. So I think it's a great result, and you will see this in the presentation of Mathieu later in this week. Here I will present another way to introduce this dependence, and it's by volume sampling. An indirect way to control the eigenvalues of the gram matrix and to push up the minimal eigenvalue of the gram is to maximize its determinant. Okay, this is one way. The benefit of doing this is because then the sampling will be easier. Okay, you will understand this. Okay, so we could try to maximize the determinant, to choose points such that it maximizes the determinant of the gram. Okay, this is a deterministic approach, and it is known in design of experiments as d-optimal design. And it's related also in linear algebra to a concept which is called maximum volume concept, okay, that have been used for many purposes, in particular low-rank approximation of matrices. But this is a deterministic route, okay, with many computational difficulties. This problem of optimization is known to be NP-hard. So there are algorithms to deal with this, but and some heuristics. But I will follow here a random route where instead of maximizing the determinant, we will draw samples according to a distribution of a set of m points, a distribution which has a density proportional to the determinant of the gram, and a reference measure here, which is the IID, optimal sampling measures that we have seen before. So simultaneously, we will try to promote by sampling high determinant of the gram and a high likelihood relatively to the optimal sampling measure in the IID setting. Okay? So in fact, we recognize in this distribution something known in statistics. It's a determinantal point process for the space Vm and the reference measure mu. namely it's a projection determinantal point process. You can rewrite the expression we have seen before in this way, where here appears a feature map, determinant of phi transpose phi, and the reference measure. And you can see clearly with this expression that the density drops down to 0 if you have two points equal, okay? Or even more, if you have phi xi equal to phi xj for I different from j, then you will have these determinants dropping to 0. So sampling from this distribution avoids sampling 2 times the same features, okay? So it promotes diversity in the selection of the features. We can prove that the marginals are all equal to the optimal IID sampling measure, but you have a dependence, okay? You have marginals equal to the optimal distribution we have seen before in the independent setting, plus a repulsion between the points. And a very interesting property of this distribution is that the conditional distribution of a point given the first points, okay, it is known explicitly. And so you have a natural sequential sampling algorithm that is feasible, okay? It's computationally viable to sample from this distribution. Okay, this was for a number of samples equal to the number of parameters. Now the question, but this does not guarantee stability of your gram with high probability. So the question is how to improve stability. What you can do is add to these m points n minus m IID samples from the initial measure mu. This corresponds to continuous volume sampling, okay? So this is this, but just now we have a distribution over n points. This is a natural approach for classical least squares, where non-weighted least squares. You can use this, but in fact you will have the same bad performance as classical least squares, okay? It will have the same drawbacks as classical versus optimal least squares. So what you can do is either take the m points from the DPP plus n minus m points from the optimal sampling distribution that we have seen in the independent setting. Okay, so the distribution is like this, determinant of the gram and times the product of the optimal sampling distribution nu m, n times. And this is called the volume rescale sampling proposed by, recently by Derezinski. It has a very nice property, a quite surprising property, that the approximation that is provided in average is equal to the best approximation in your space Vm, okay? So it provides an unbiased projection. But we realize in practice that the performance is similar to IID optimal sampling, because in order to reach stability, you need a lot of additional samples, and essentially, asymptotically, it's like drawing independent samples from the optimal distribution um, okay? So another way to get stability is, instead of adding independent samples, you will repeat sampling from the DPP, okay? So you draw multiple times m points independently, and with this you get a result, a quasi-optimality in expectation, which is similar to what we have seen before, with conditions on the number of samples that are similar to what we have seen before. We were not able to really show theoretically that we can gain in terms of sampling complexity, but I will show you that the performance in practice appears to be better. So there is still a gap in theory to really prove that this strategy is better than the previous one. But here it's an illustration of what happens in practice. It's a polynomial approximation. And I plot here the probability that the spectrum of the gram is contained in the interval 1/2, 3/2, okay, as a function of m, the dimension of your space Vm, and number of samples. This is for classical sampling, where you can see that for a given dimension, let's say 30, okay, so it's degree 29 for the polynomials, you will need a number of samples which is very high in order to get a probability which is high to be contained in this interval. So I should say that black is probability 0, white is probability 1 to have stability, okay? So you want to be in the right region. For optimal sampling but independent samples, you can see that it's greatly improved classical sampling. So, but look at the range here. So for 30 here, for the dimension of your space, you will need, let's say, 600, 700 for the number of samples in order to get with reasonable probabilities the stability of the graph. This is for volume rescale sampling of Derezinski, where you see it's very similar to IID sampling. The fact that you have in these samples m points that are drawn with a repulsion from the DPP, it does not improve so much. And this is with the repetition, independent repetition of determinantal point processes, where here you have a gap, you really gain. So still for 30, you need, let's say, 200 samples, but it's more reasonable than going to this huge number of samples that you see here. Okay? So still some theoretical result to obtain, but it's quite promising in application. You can start from a low number of samples that leads to stability of the gram. So question now is how to extend these ideas to nonlinear approximation. So here my set in which I will approximate the function, I denoted m. It's described by m parameters. And we would like to provide an approximation which is close to the best approximation error. And the bad news is that the required number of samples for achieving this task can be much, much higher than the number of parameters, okay, for many nonlinear classes. And in fact, this has been proved for several nonlinear approximation tools, in particular for neural networks by Gross and Voigtländer, and later by Hegel, Schneider, and Trunschke for tensor networks. What they have proved is that there are concrete quantitative results that show that there is a theory to practice gap, in the sense that even if your function can be approximated with a fast rate with your nonlinear approximation tool, fast rate in terms of the number of parameters, the number of samples you will need to achieve this performance in practice can be exponential in the number in the dimension of your problem. Okay, so these are papers essentially related to high-dimensional approximation. But yet, there are results, in particular in the work of Hegel, Schneider, and Trunschke, and also in a work by Ben Adcock, which is here in the room, that have shown that you can get quasi-optimality results if the number of samples is greater than a constant that depends on your manifold, and which is a generalization of the inverse Christoffel function we have seen before in the linear setting. And it has an expression that looks like what we have seen before, supremum of the inverse of the weight function times a function that can be interpreted as this generalized Christoffel function. Okay? And from this condition for getting quasi-optimality, you can derive an optimal sampling strategy for nonlinear manifolds. Okay? You can select W such as you minimize this. Okay? So you will sample IID according to this kind of generalized inverse Christoffel function. This is feasible, but for most of the interesting nonlinear approximation tools, tensor networks, neural networks, you realize that it has no real benefit compared to just doing classical sampling. And this, in particular, has been proved by Hegel, Schneider, and Trunschke. Yeah, it's a paper by Trunschke in 22 that if you consider for M the set of low-rank tensors in a tensor product space U tensorized D times, okay, so you consider any set of low-rank tensors in this, even rank 1 tensors, then the constant that you see here associated with this low-dimensional manifold is equal to the constants of the background tensor product space. Okay, so this constant doesn't see the nonlinear structure of M. Okay, it just sees the background linear space, which has a dimension which is exponential in D. So the number of samples will be exponential in D for this task, even if you approximate in a very low-dimensional manifold of a tensor space. So the conclusion of this, partial conclusion, I would say, is that more assumptions are are needed on functions, and dedicated algorithms have to be provided. And I have the feeling that at least for the nonlinear approximation classes, neural networks, tensor networks, the only route is to provide adaptive algorithms that are adaptive to the function. And so here I will present a recent work with Robert Gruhlke and Philipp Trunschke, where we try to exploit the linear approximation machinery in a nonlinear world. And how we do this, we rely on the introduction of a natural gradient algorithm. So what is it? So we consider a differentiable manifold M, and we want to optimize a certain loss function. So think for the moment as 1/2 of the square of the distance between the function f and your approximation. You want to optimize this, and you introduce a natural gradient descent. What is it? So it will look at an iterative algorithm writing like this. So you have your manifold here, the current iterate here, fk, the target function here, f. So you start by approximating your manifold by an affine space fk plus vk. So vk is kind of linearization of your manifold at the point fk. You project the error f minus fk onto this linear space vk. Okay, so you get this jk. It's a projection, in fact, of the gradient of your loss function, which is here the difference between fk and f. And you introduce eventually a step size, okay? And then because you have moved outside the manifold, you need a retraction step. You need a map rk that will push back your point here onto the manifold, okay? So this is a very simple gradient descent, but this algorithm works in function spaces here, okay? Not in parameter spaces as it is usually presented in approximation with nonlinear tools. We work in a functional setting. Here, the projection onto the linear space vk will be performed with the machinery I have presented in the first part, okay? So we will draw samples optimally for the current space vk that you have selected at this step, and you will project the error and get this direction vk. Concerning the space vk, if you have a differentiable manifold, linearizable manifold, we don't need to have a manifold in a strict geometrical sense. We just need a way to linearize locally the manifold. So if you have a manifold that is described by m parameters, with f being a representation map that gives for a given value of the parameter a function in your function space. If you have this, and if the parameterization map f is differentiable with respect to theta, you can define a linearized space that if M is a differentiable manifold, we call this a tangent space, the tangent space to the manifold at the point fk. And this is no more than the span of a set of basis functions obtained by the partial derivatives of your representation map with respect to your parameters, okay? So this is a picture of this. So you can select this linearized space around your space around the point fk, or eventually a subspace of this if this space is too huge. About the retraction, so there are some family of nonlinear manifolds for which you have natural retractions, controlled retractions. If you don't have, and this is the case, for example, for neural networks, there is no known controlled retraction for neural networks. So a natural retraction is then this retraction that will define the retraction of this point fk minus sk gk as the function represented by theta k, the current value of the parameters, minus some move in the parameter space. Okay, so you will move in the parameter space. How do you move? You take the function jk that you have computed from your least square approximation in the function space. It has some parameters on the basis of function psi, which generate the tangent space. And you take these values of the parameters to make your move here in the parameter space. And then you push back on your manifold through the representation map. This is one way to do retraction, but it's relatively hard to control, okay? There is no guarantee of a control here, and this in practice, for neural network at least, requires some adaptivity in the step size in order to control what you do at this step. I would like to mention that if you move in the parameter space in a very naive way, but natural way, where you take the generating system of your linear space, Vk, and you project with an empirical norm the residual Fk minus F on this basis. So it is rewritten here as an average of psi xi times the difference between Fk, the current iterate, and your function. This is no more than the gradient with respect to the parameters of an empirical loss function. Okay, so an empirical loss function written in terms of the parameters. So this is the usual way statistically to optimize on neural networks, in particular on nonlinear approximation classes. You estimate your loss function, and you write your objective function as a function of the parameters. Okay, and then you do a gradient descent in the parameter space, and this gives you this definition of the move in the parameter space. Well, this is known as stochastic gradient descent, or because I take n samples per step, it's more a batch stochastic gradient descent. So what is the problem with this stochastic gradient descent is that, in general, this psi, which is just the gradient of your representation map F, is far from being an orthonormal basis. It's just a generating system of a space, but it can have many redundancies. It can have strong linear dependency between the functions, such that what you compute here, the gamma k, is far from being the coefficients of a good projections in the space Vk. So you are far from the orthogonal projection. So what we do, in fact, you can see what we do, the natural gradient descent, and plugging this optimal sampling strategy is kind of preconditioning the stochastic gradient descent. Okay, this is one way to see natural gradient. It's a way to precondition your stochastic gradient descent. Okay. How much time? Okay, 8 minutes. We have a few results, a few theoretical guarantees for this strategy, under, of course, some assumption. The first is about the projection that you perform, the empirical projection onto your space Vk has to satisfy a condition on the bias. So I mean, p hat, this empirical projection, must, in expectation, be not too far from the orthogonal projection. So this is translated in this relation with a constant CB related to this bias. And you need also a bound on the variance on your projector. But just to do it quickly, the strategies I have presented in the first part, IID, sampling from optimal measures, DPP, repeated DPP, all of these satisfy this property, okay? And the good thing with optimal sampling strategy is that you have a control of these two terms, CB and CV, okay? And you have a control of this with a number of samples, which is of the order of d log d, where d is the dimension of the current space Vk. The second condition is classical when you analyze algorithm on manifolds, is that you need some restriction on your manifolds. It's more precisely condition on the curvature of your manifold. Okay, your manifold should not be too crazy, and so it translates into a condition that the loss function after the retraction of Fk plus some function must be bounded by the loss of Fk plus j plus some term. So after retraction, you should not deteriorate too much the value of the loss, and this term, the loss here, should be of the second order in the norm of j. And here you have a parameter bk that has to be selected as a little o of the step size. Okay, so this is something that you can guarantee with classical assumption on curvature, and more precisely on the reach of the manifold, which is a classical notion for differentiable manifolds. So I don't get into the detail, but these conditions are known for classical manifolds. And I should say that for neural networks, for example, we have no such relation. Okay, this condition can guide an adaptive strategy in order to select a step size, in order to to satisfy this property, but there is no a priori result on many interesting nonlinear manifolds. So the convergence analysis starts with defining a filtration associated with the sample generated all along the iterations. And what we can prove is that in expectation, the loss at step k plus 1, given the fk, this is the sigma algebra generated by all samples generated previously, in average, the loss is less than the loss at the previous step, plus some term, where you see here a term which is of second order in the step size. Interesting term here is a term which is of first order in the step size, with a parameter gamma k, which is here. And that depends on the bias of your projection. For unbiased projection, you don't have this term. You have just here minus step size times this. And you can prove that if your step size is sufficiently small, you will have this term, which is negative. Okay, so you can get a decrease in average with a sufficiently small step size. And using classical martingale theory by Robbins and Sigmund, you can even prove almost sure convergence. You have this relation. In expectation, you have a decrease. But from this theory, martingale theory, from this, you deduce an almost sure convergence of your algorithm to what? To a stationary point of the optimization problem. Okay, of course, no global optimization results, just convergence to a stationary point. What are the rates? So you can look at the paper. You will have a deep analysis analyzing different situations where we can prove that we are between algebraic rates of classical gradient descent and the worst rate of stochastic gradient descent, depending on the situations. And in favorable cases, in particular recovery setting where your function is in the manifold, and assuming a little bit more in the manifold, like strong convexity or weaker Polyap-Lyajedovich condition, you can get even an exponential rate that is achieved in particular by gradient descent, but never by stochastic gradient descent. So it's a strategy lying between a classical gradient descent and a stochastic gradient descent. Okay, so, and there is an analysis also for bias projection under more technical things on the behavior of this term. I don't get into this. So I talk a lot on L2 approximation, a loss function related to some norm at least, but you can generalize this to other risk functional under classical smoothness and convexity assumptions on the functions. Okay, so this is an illustration. You will find many illustrations in the paper on the behavior of this algorithm. A few words, maybe at the end on the linear approximation again, but because we have seen that we have some guarantee in expectation with the machinery I've presented first. You can exploit this in nonlinear approximation, where you just need this quasi-optimality in expectation at each step of an algorithm. But in many practical situations, it's very important to have almost sure guarantee, because having just in average some quasi-optimality is many applications not enough, because when you run one time your algorithm, you don't know really if you are good or not. Okay, so you would like to have almost sure guarantee. And for this, you will have to modify your least square projection and the distribution according to which you optimize. You remember this relation about the error. You have the error bounded by the error with respect to any function in the space Vm plus inverse of minimal eigenvalue. And here's the empirical norm of the difference between f minus g. So we need to control this empirical norm, and we need to control the minimal eigenvalue of the gram. You need both. And you can, if you make more assumption on the function f, if you assume that your function f is in subspace H of functions for which you have a control that the empirical norm is bounded by this H norm of your function j, then you can get a quasi-optimality property. But quasi-optimality, it's not really quasi-optimality in the sense that here you have the L2 norm, and here you have the H norm. Okay? Yeah, okay. So I will finish here about saying that in order to get this, you need some assumption on the classes of function, and you will need to modify the distribution according to which you sample. So you can find some details in the work by myself and Michel. So you will see that you need to introduce some mixture between the optimal sampling distribution and something related to the space in which your function lives. And last advertisement, I don't go into the detail, I stop here, but you can go even further if you assume that your function is in a reproducing kernel Hilbert space. By modifying the least square functional and taking into account the kernel of your RKHS, so it's a standard way to do kind of least square approximation in our RKHS. If you do this, you will get quasi-optimality in the space H. And this is really quasi-optimality because here you see the H norm and here's the H norm, okay? And so we have proposed in this paper, it's recently, in fact, it's put it on arXiv last week, so you can see that there are sampling strategy derives from this theory, and that have great performance in practice. I just put the references of the talk here. Okay, thanks for your attention.
I have a comment, kind of brief comment. Now it is well understood that you can get recovery if you have good discretization. And there are many papers now in that direction. So basically, if you have good discretization, and you can use different ways to get good discretization. It could be deterministic, could be probabilistic, then more or less automatically you get good recovery. And this linear and nonlinear. In the case of nonlinear, we need universal discretization and so on. So I don't know if you're aware of that direction.
Yeah, but I mean,
but in that case, probably it will be.
I'm mostly interested in nonlinear approximation in high dimension, and for which there are these theoretical gaps that you have seen. Okay, there is no universal discretization, no uniform universal sampling algorithm to achieve this kind of performance.
There are some. I mean, at least depending on the problem, you can use greedy algorithms, which will prove that these are very good. For nonlinear recovery.
No, but for tensor networks and for neural networks, that was the main motivation of this work in high dimension, there is nothing. There is nothing guaranteed today. I agree, but for most linear approximation tools, splines, polynomials, and so on, they are known deterministic and stochastic approaches. Okay, so for many tools, there are some, of course, some state-of-the-art sampling and discretization techniques, but the motivation here was, what to do with these nonlinear classes that we manipulate today and for which there is nothing known. So the illustration in the papers are for neural networks, but we have done some work on tensor networks also, and so there is no. This is an open problem today.
Just one short question. Yeah. So
Comment more on the last part of the talk, especially about using reproducing kernel Hilbert space or assuming that the function. What is the difference between what you are showing?
In the last year, the modification it's no more a weighted least square functional here in the usual sense, where you have an average of the squared error weighted. Okay, here this is a matrix, which is here the inverse of the kernel matrix.
sorry.
Okay, this is not classical least squares.
Yeah, maybe you can talk after the like.
Work that was already done.
Yeah.
Because there is work that's already done.
Yeah, sorry.
Yeah, we can discuss later.
Yeah, we are running out of time. So